Hi, I'm Mr. Zapone, and in this screencast we're going to talk about periodic trends. And we're going to look at trends in nuclear charge, electron shielding, atomic size, ionization energy, electronegativity, and chemical reactivity. And we're going to do all of these things in terms of Coulomb's law. And we're going to take a detailed look at Coulomb's law, and we'll go through the inverse square law, and we'll look at all of these trends. So we're going to start with Coulomb's law. And Coulomb's law is an inverse square law, and these are very important in science. It's a law of physics describing the electrostatic interaction between electrically charged particles. And really what Coulomb's law is, it's the electrostatic force. And you probably know that opposite charges attract, like charges repel. So if we were to look down here, this kind of shows what would happen if you had two positive charges next to each other. They would repulse one another. And if you had two negatively charged spheres, or say electrons, next to one another, they would also repel or repulse one another because like charges repel. And opposite charges end up attracting. So a proton and an electron would be attracted to one another. And that's kind of what holds an atom together. You have protons in the nucleus with a positive charge, and they're surrounded by negative electrons, which are attracted electrostatically to the nucleus. And before we move on, I want to take a deeper look at what an inverse square law really is. Coulomb's law says that the electrostatic force, the amount of the pull or pushing, the repulsion or the attraction of the electrostatic force, is going to be equal to K times Q1 times Q2 divided by R squared. And what does that really mean? Well, all it really means is that the amount of charge each object has, you multiply them together and you divide it by their distance squared. That kind of tells you the magnitude of the electrostatic force. K is going to be a constant. It's always going to be the same value. So for our purposes and what we're going to do, we're kind of going to ignore it. But what Coulomb's law really says, the greater the charge, the greater the force. The greater the electric charge, the greater the force. That's Q1 and Q2 between these two particles. And the closer the particles, the stronger the force. So when you have particles that are close together, there's going to be more force. If you have particles that are separated by a large distance, there will be a weaker electrostatic force. And that's all due to this R squared right here. And you can kind of think of this in terms of magnets. When you put two magnets close together, boom, they click together. But when they're really far apart, they're not really that attracted to one another. Because magnetism, or the magnetic force, is going to kind of obey this inverse square law as well. So let's kind of do an example here and see what we mean by this. So this might look a little confusing at first, but I'm going to try to simplify it. Let's say we have an electron, which has a charge of -1, and a proton, which has a charge of +1. And they're separated by a distance of 1. We're not even going to put units in for now. I just want you to understand what inverse square means. So let's see if we can calculate the force. And since they are opposite charges, we know that force is going to be attractive. So what is Q1? Well, Q1 is going to be -1. And we're going to multiply that times Q2. And again, we're ignoring K because it's just a constant. It doesn't really matter. And that's going to be a +1. And the distance separating them is 1. So 1 squared. And -1 times a +1 is going to be a -1 over 1 squared, which is 1. So our final answer is -1. And what I'm going to tell you, that negative sign, all it really means right now is that the force is attractive between these two particles. They will be attracted to one another. If it was positive, I would say that they're going to repulse one another. If you had two protons, it would be positive. If you had two electrons, it would be positive. A negative times a negative. So we end up with a value F equals 1. Now what happens if we double the distance between these two particles? Well, we have the same numerator. The charge of the first electron is still -1 multiplied by a +1. What happens to the radius? Well, we doubled it. It's now going to be 2 squared. And -1 times 1 is going to equal a -1 over 4. So this is the key to the inverse square law. When you double the distance between something, the force doesn't decrease by double the amount. It decreases by a fourth, or 4 times as much it decreases by. The force is a fourth as much. And the same thing's going to happen here. If you triple the distance, the force will not become 3 times as weak. It's actually going to become 9 times weaker. That's the inverse square law. It means there isn't a linear relationship between force and distance. The relationship is an inverse of a square. So we could easily do this problem out, or you could say even if the radius was 4, it's going to be 1 over 16, or if it was 5, 1 over 25. That's the inverse square law. It merely states that as distance increases, the force is decreasing by the square of the radius. Force, to use fancy science terminology, is proportional to 1 over r squared. That is the inverse square law, and that is part of Coulomb's law. The reason I'm going over the inverse square law is because, as we're going to see, Coulomb's law is extremely important in chemistry. It's kind of what's holding an atom together. It explains all our periodic trends. And not only is it a part of the electrostatic force, but also the gravitational force obeys the inverse square law. In classical physics, the magnetic force does as well. The intensity of sound also obeys this. How loud sound is, how loud you hear it. It decreases with a factor proportional to 1 over the distance squared. Same thing with the intensity of light or field strength. So the inverse square law is very important in science. A lot of different formulas and physical properties obey this law. So again, this image is kind of showing that if you have light being emitted from a source, this is kind of how bright the light would be at a radius of r, or 1. If you double the radius, the intensity of that light would only be a fourth of the amount. All this light has to spread over this entire area. And if you triple the radius, it would only be a ninth of the amount. Because again, it is proportional to 1 over r squared. That is the inverse square law. That's how Coulomb's law behaves. So now we're going to look at something called nuclear charge. And what is nuclear charge? Well, it's just a total electric charge in the nucleus of an atom. It's really equal to the number of protons in an atom. And it's the nucleus, the positive charge of the nucleus, that is what's holding the electrons into the atom. So what happens in nuclear charge as we go across the periodic table? Well, it's kind of simple. Don't overthink this. It increases. Hydrogen has 1 proton. As you go across, helium has 2 protons. Lithium has 3. Beryllium has 4. 5. The number of protons is increasing as we go across. So the total charge in the nucleus of an atom is increasing. Likewise, as we go down in the periodic table, nuclear charge is also increasing. Helium has 1 proton. Lithium has 3. Sodium has 11. And potassium has 19. It just keeps going on. It's actually increasing by a larger amount going down. But either way, the important part is to realize that the total positive charge of a nucleus is getting bigger no matter which way we go on the periodic table. So now we're going to look at some trends. And right here I've drawn the first 3 elements in column 1A going down the periodic table. Hydrogen, lithium, sodium, then potassium, and so on. What we're going to do is we're going to draw Bohr diagrams, and we're going to represent the electrons by energy levels in these atoms, and we're going to see if we can kind of glean a trend from this. So hydrogen, which has an electron configuration of 1s1, has only 1 electron, and it's in the first energy level, right there. 1s1, 1 electron. Lithium has 3 electrons, 3 protons, 3 electrons. and you end up with 2 electrons. And, oops, sorry, I clicked that. But you end up with 2 electrons in the first energy level and 1 in the second energy level. 1s2, 2s1. There's 2 electrons in this s, 1 in the second. And then when we go down to sodium, sodium has 11 protons, also 11 electrons. So again, our 1s2, there's 2 electrons in the first energy level. This second energy level, which is both the 2s and the 2p6, has 8 electrons. This whole energy level is full. And there's 1 extra electron going to the 3s1. Now in my class, we've already seen that there's a repeating pattern of electron configurations as you go down. Hydrogen's 1s1, it ends in. Lithium ends in 2s1. Sodium's 3s1. Obviously potassium's 4s1, and then 5s1, 6s1, and 7s1. So there's a pattern there. And the other pattern I want you to see here is as you go down a group or a column in the periodic table, the number of energy levels, or these rings, each one of these rings represents an energy level. The number of energy levels is increasing, and that's fairly obvious if you know how to draw a Bohr diagram, and you're kind of familiar with electron configurations, as you should be. Another way to look at this is in terms of periods. The periodic table has 7 rows, and each row is going to correspond to one of these circles. Hydrogen has 1 circle, 1 energy level. Lithium has 2 circles, 2 energy levels. Sodium has 3. Potassium have 4. Rubidium 5, cesium 6, and francium will have 7. As you go down the periodic table, each row corresponds to a new energy level. So it's kind of something we looked at earlier, just a little refresher there, but we know that energy levels are increasing as we go down. And again, this is something we saw when we did electron configurations. Kind of increases down, 1s1, 2s1, 3s1, 4, all the way over. And you might be a little confused by these D block elements. If this is row 4, how come these aren't in the 4? Well, you just kind of got to remember that the 4s fills up before the 3d. So technically these do have 4 rings. It's just that the part of the 4th shell filled up before the 3rd finished because of this Aufbau building up thing we looked at. So technically each one of these rows represents an energy level in our Bohr diagrams. These are our blocks. Students, please don't fart. FPDF, remember? 4 blocks. S block over here, P here, D, and F down here. So while we have this slide up, let me ask you a question about atomic size. What do you think happens to the size of atoms as we go down a column in the periodic table? Oops, my pen is giving me issues. And what we see here is we have hydrogen with 1 energy level. Lithium has two energy levels. Sodium has 3. I mean, if you just look at the size of these, even though these aren't drawn to scale, but the atom is generally just getting bigger. There's more electrons. There's more energy levels. Electrons are getting further out from the nucleus. So atomic size must get bigger as we go down the periodic table. Kind of a trend in atomic size, just because the number of energy levels is increasing. So also the size of the atom must also increase. So if we look over here, we have a few trends. And again, as we go across the periodic table, the number of protons increases. So the charge in the nucleus, the nuclear charge, is getting bigger. Nuclear charge is getting bigger as you go down the periodic table. And also atomic size increases as we go down the periodic table. Going down, elements are getting bigger all throughout the periodic table. Oxygen is bigger, or oxygen is smaller than sulfur. Hydrogen is smaller than lithium, which is smaller than sodium, and so on. And this is kind of a pictorial representation of this, the size of atoms. Hydrogen is smaller than lithium, but sodium is bigger than lithium. Potassium is bigger than sodium. Potassium is bigger than calcium and scandium going all the way over. So atoms get smaller going from left to right, bigger going from top to bottom. This might be a little confusing going to the right because as you go to the right, you're getting more protons, you're getting more neutrons, you're getting more electrons in the atom. There's more particles in the atom even as you're going over it. So why do they get smaller? And we'll talk about that in a bit in terms of Coulomb's law. But before we do that, we kind of looked at what happens to energy levels and electrons as you go down a periodic table. What happens to them as you go across a period or across a row in the periodic table? So here we have the second period in the periodic table. Lithium, beryllium, boron, carbon, or beryllium, boron, carbon, boron, nitrogen, oxygen, fluorine, Sorry, I had a brain fart moment. But lithium, number 3 on the periodic table. 3 electrons, 3 protons in the nucleus, a +3 charge. 2 electrons in the first energy level, 1 in the second. Now beryllium is going to have 4 total electrons, so it's going to have the same configuration as lithium, but there's going to be 1 extra electron in this second ring. And that's exactly what we see, a +4 and 2 electrons here. Boron's going to have 1 additional electron, and the atomic number of boron is incorrect, so is beryllium. But what we're going to see is beryllium is going to have 1 additional electron in here. So what's happening to the number of electron energy levels as you go across the periodic table? The number of energy levels is remaining constant as you go across a row in the periodic table. We're in this second ring. We're going to stay in this second ring all the way across this whole row in the periodic table. We're just going to keep adding electrons on it until it gets full. Once it's full, we're actually going to add another ring on, and we'd be in the next row of the periodic table. We'd be in the sodium row. So as you go across the periodic table, the number of energy levels remains constant. As you go down, energy levels are increasing. As you go across, they're remaining constant. So let's use this principle to look at something called electron shielding. And this is very, very important. Electrons in an atom can shield each other from the pull of the nucleus. So according to the electrostatic force, or Coulomb's law, this has a plus charge. All these electrons are minus charges. So there is an electrostatic attraction to them. This is being attracted to the nucleus. All these electrons are being drawn in, opposites attract. But this electron right here, sure, the nucleus is pulling it in. But what is this electron doing right here? What do like charges do? This electron's saying, whoa, 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 buddy, get away from me. It's actually repelling or repulsing it. So this electron right here does not feel the entire pull of the nucleus because it's being shielded by this one. And this electron's actually being shielded by both of these because they're moving around at high speeds. So electrons in this energy level are being repulsed by 2 electrons in the previous energy level. It only gets worse for this guy out here. He's in the outermost energy level. All of these electrons are basically saying, hey buddy, get away from us. They're all repulsing him. Sure, the nucleus is pulling this guy in, but at the same time, all these electrons that are moving around, they're repulsing him. And this is what we call electron shielding. This electron is not feeling the full pull of the nucleus because the other electrons in between it are kind of pushing it out because opposites attract, but like charges, 2 negative charges, will repel one another. So that is electron shielding. It's going to become very, very important throughout the rest of this slideshow. So to summarize what we looked at, as you go down a group, electron shielding increases as we go down. There's more shielding, right? Because you have more energy levels. This electron right here is being shielded by 2 electrons inside of it. This one is being shielded by all 10 of these. And if you went down to potassium, there would be a whole other energy level. And this one would all be full. And this one lonely electron out here would be shielded by all of these. So as you go down a group, as you go down in the periodic table, Electron shielding increases because the energy levels are increasing. As you go across a period, what happens to electron shielding? It stays constant because the energy levels stay constant. This electron is being shielded by these two electrons inside of it. These two electrons are still only being shielded by these two electrons. These three electrons for boron are being shielded by these two. So as we go across the periodic table, shielding is constant, and these two things are going to be huge for the rest of our understanding of the periodic table. So to summarize some of our trends, again, nuclear charge increases, proton number increases as we go across, electron shielding remains constant going across. Atomic size, we kind of saw that it gets smaller, but we're going to explain why now. Nuclear charge increases going down, shielding increases going down. The repulsion from like charges is increasing because there's more electron energy levels. And of course, atomic size is increasing because there's more energy levels. So now let's look at atomic size. As we go across a period, atomic size decreases because the pull of the nucleus, or the total nuclear charge, increases, but electron shielding remains constant. So the nucleus is able to pull the electrons closer, and this is Coulomb's law. This nucleus right here is pulling these, it's kind of pulling all of these electrons in with a force of +3. Now this one electron is being shielded by 2. So it's not feeling the total force, but this nucleus is pulling in with the force of +4. It's pulling in all these electrons with a +4. These electrons are also only being shielded by 2, but there's a stronger pull of the nucleus with the same amount of shielding. So the atom's able to pull in a little tighter. This is a +5 charge. Same level of shielding, no extra repulsion, so it's able to pull the atom in even tighter still. That's why atomic size decreases as you go across the periodic table. Because nuclear charge increases, but electron shielding is constant. So the nucleus gets stronger. It's able to pull the electrons closer. There's no additional electron repulsion to balance or counterbalance the increased nuclear charge. So that is why atoms get smaller going across. Despite the fact that there's more particles in it, there's more electrons, more protons, and more neutrons. Yet the atom is still smaller. So we added in up here, atomic size decreases to our other trends. Now we're going to look at something called first ionization energy. And this is the energy required to remove the outermost electron from an atom. And if we were to look at this atom right here, this is, I hope you guessed, sodium has a +11 charge. That means it's 11 on the periodic table. One valence electron, so you know it must be in column 1A. Well, the first ionization energy is going to be the energy required to take this electron right here and basically remove it from the atom, to get rid of it. And what's keeping this electron here? Well, the nucleus. This nucleus right here is basically pulling it in through Coulomb's law. Opposites are attracting. While simultaneously, all these other electrons are kind of saying, hey buddy, get away from me. So as you might guess, this outer electron is only loosely held. But this is ionization energy. It would take some force or some energy to pull this electron out of this atom because the nucleus is holding it. Even though there is a lot of shielding, the nucleus is still kind of attracting and keeping it there. So it would require a little bit of energy to basically rip this electron off and form an ion. So that is what ionization energy is, and we're going to kind of look at some trends now with that. And this slide is just chock full of stuff, so let's go through it. As you go down a group, first ionization energy decreases. Now remember, ionization energy is the amount of energy you need to remove an electron. So what this is saying By saying ionization energy is decreasing, you're saying it gets easier to remove this electron. You need less energy as you go down to take this electron. And this should make perfect sense to you right now. Because what do you get as you go down? You get more shielding. You get more energy levels, more shielding. This electron right here is going to be really easy to remove. Even though the nucleus is pulling it in, all these other electrons are repulsing it. There's so many electrons. In addition to that, this electron is actually really far from the nucleus. And we have that crazy inverse square law. This thing is really far from the nucleus, so the electrostatic force is actually going to be pretty weak if you think about the 1 over r squared relationship. In addition to that, you have all these electrons repulsing it. So this electron is going to be really easy to remove. This one will be a little bit harder. This one will be even harder still. So additional electron shielding and increased distance from the nucleus makes removing the outermost electron much easier. So let's look at the opposite case now. What happens as we go across the periodic table? As you go across the period, first ionization energy increases. And what that means in simple terms is that it gets harder to remove this electron as you go across. It's harder to move, or it's harder to get rid of this beryllium electron than it is the lithium one. And it's even harder still to remove one of these electrons from boron. And why is that the case? Well, as you go across the periodic table, nuclear charge is increasing. The pull of the nucleus is getting stronger. It's increasing. But there's no additional shielding. So this nucleus is actually just pulling these electrons stronger and stronger. So it makes it harder and harder to remove an electron as you go across. So that, if you kind of look at electron shielding and nuclear charge, and they're based on Coulomb's law, it explains trends in ionization energy level. You don't really have to necessarily memorize this. If you know what ionization energy means, you should kind of be able to figure out what's happening just by thinking about nuclear charge and electron energy levels. It's going to be much harder to take an electron as you go across because the pull of the nucleus is pulling things in tighter. There isn't any extra or additional electron shielding. It's remaining constant. And here we see a sort of attempted three-dimensional diagram of trends in ionization energy, and this actually has numbers on there which should be measured in kilojoules per mole. It would take 1,312 units of energy, which are kilojoules, to remove the electron from hydrogen. And if we were to go down to lithium, it only takes 520, 496, 419. As you see, as you go down, ionization energy is decreasing, which means it's becoming easier to take that electron because there's more shielding. In general, as you go across the periodic table, they're getting taller. It's becoming harder to take an electron. Becoming much, much, much harder to take an electron. And if you look at these noble gases, you probably know or have seen that these are chemically inert or non-reactive, we call them. So they have very high ionization energies, and you know they have a full octet. All of these have 8 valence electrons. They don't really want to lose or gain electrons. So that's why these energies are so high compared to a lot of the other elements, because they're all relatively pretty stable. They don't want to lose electrons or gain them, so it's really, really hard to take an electron from one of these things because their configuration is stable. But other than that, those are our trends in ionization energy. So if we plot this next to our other trends, we see that as we go across, first ionization energy is increasing. And that means it's getting harder and harder to remove an electron, because ionization energy is the energy you need to pull an electron, the outermost electron from the atom. And as you go down, ionization energy is decreasing. It becomes much, much easier to remove that outermost electron and make it an ion. It becomes much, much easier. You don't need a lot of energy, so it's decreasing. Now we're going to look at something called electronegativity. And electronegativity is a measure of an atom or a group of atoms' tendency to attract electrons. So some atoms are going to want to attract electrons. And what in an atom is going to make it want to attract electrons? Well, the nucleus. Electrons have a negative charge. The nucleus is positive. So how likely an atom is to attract electrons is going to depend on, well, nuclear charge and how many electrons are in the way. It's going to be hard to attract an electron here because even though the nucleus is going to pull it in if you had a nearby electron, all these other electrons are basically going to say, hey, buddy, get out of here. So we have to kind of look at nuclear charge and electron shielding to see what the electronegativity of an atom will be. And we'll do that right now. As you go down a group, electronegativity decreases. Why does it decrease? Additional electron shielding. As we go down, there's more shielding. An increased distance from the nucleus makes adding a new electron more difficult. So as you're going down the periodic table, you have more energy levels. You have more electron shielding. So an electron here would probably be easier to go here because it's not that far from the nucleus. There's not a lot of electrons saying, get away from me. Over here, now we have a further distance from the nucleus. And remember that 1 over r squared, the further you are from the nucleus, the pull is decreasing by a factor of the square. And if you had one here, it's going to be really hard for this electron to go in there because you have all of these electrons here basically saying, hey, buddy, we don't want you here with us. We're full. Get away from us. We don't need you. So that's kind of what we have to look at. As you go down, there's additional electron shielding and obviously increasing distance from the nucleus. Coulomb's law is proportional. Electrostatic force is proportional to 1 over r squared. So it's really hard to add an electron as you go down the periodic table. It becomes increasingly difficult to add an electron. Now what happens to electronegativity as you go across a period in the periodic table? Well, it's going to increase. Increasing nuclear charge. So the nucleus or the charge of the nucleus increases as we go across. There's more nuclear charge. There's a greater pull as you go across. But there isn't any additional electron shielding. So the nucleus is getting stronger and stronger and stronger. It's pulling more and more and more as you go across the periodic table. So it becomes easier to add an electron as you go over here. Boron would add an electron. Or actually as you go further over. But it becomes easier as you go over, as you get to the far right side of the periodic table, negating noble gases, it becomes very, very easy to add electrons. And again, that's due to the nuclear charge increasing and a lack of additional electron shielding. And fluorine we call the most electronegative element. And this is kind of a chart of electronegativity. And don't worry about the scale. We'll see the scale after we cover covalent bonding. We're going to kind of see how exactly we know whether something's ionic or covalent besides the general metal, non-metal rule. So fluorine has an electronegativity of 4, and this is the highest on the periodic table. It kind of makes sense. Chlorine has more energy levels. Bromine has more energy levels. Iodine has more energy. There's more shielding as you go down here. More and more shielding. So these aren't going to have, electronegativity is going to decrease as we're going down. And over here we have fluorine. In this total row, it has the highest nuclear charge. It's number 9 in the periodic table. It's a +9. So you have a really strong nucleus with a little bit of shielding, so it can really attract electrons. And that's why fluorine is often called, or it's the most reactive element on the periodic table. It has the highest electronegativity. And again, that is explained in terms of electron shielding and Coulomb's law and nuclear charge. And the noble gases, we have a question over here. What about the noble gases? Why are they blank? Well, as we said, all of these have 8 valence electrons, and they're generally considered stable. They don't want to gain or lose electrons, so we kind of blot them out. They're not actually 0, but for the most part, we're just going to ignore them here. So if we look at our trends, we're adding trends to this now. Now we have 5 trends going each way. Electronegativity increases. As you go across the periodic table, it becomes easier to grab an electron, to acquire an electron. Or atoms are more attractive. They have a tendency to be more attractive towards electrons as you go across. As you go down, electronegativity is going to decrease. It's going to be harder to take an atom. And I think I have a boo-boo over here. This should say decreases. And I think I'm going to have to fix that in every slide. Decreases. Electronegativity decreases as we go down because there is increased shielding. Increased shielding means electronegativity is going to decrease. And now we're going to look at, I believe this is the last thing, there might be one more. We're going to look at reactivity, chemical reactivity. For now, we can think of an atom's tendency to lose or gain electrons as its reactivity. So if an atom really wants to lose electrons, or if it can lose electrons easily, or gain electrons easily, we're going to call it reactive. And what that means is, we've already said that fluorine has a high electronegativity. As you go across the periodic table, you have a +9 here. There's a lot of nuclear charge. But fluorine doesn't have a lot of electron repulsion or electron shielding. So generally over here, for nonmetals, these are going to be the most reactive. They're going to most easily gain electrons. Coming down here, with metals, these are going to be the most reactive. Not because they're gaining. These don't gain electrons. They lose them very easily. Metals tend to lose electrons, and nonmetals tend to gain electrons. So you have a lot of shielding here, and one valence electron in the outer level. The shielding to nuclear charge ratio is not very good compared to over here. So these are going to lose elements, but these are going to lose elements ridiculously fast. As you're going to see, I'm going to do a demonstration where I put lithium in water, sodium in water, magnesium in water, and calcium in water. We're going to see reactivity trends, and they will bear this out. That reactivity for metals is going to increase as we go down and decrease as we go over. And then for nonmetals, it's going to increase and decrease the other way. And we'll kind of draw that out. And again, this should be decreases. Make sure that's decreases. So this is, I believe, our final slide, and there's a brief assignment on the next one. And I put Coulomb's law here again because it is super, super important in chemistry. So many trends in the periodic table and chemical reactivity, losing or gaining electrons, size of atoms, all depend on Coulomb's law. So going across, proton number increases, nuclear charge increases. Going down, proton number also increases. And I kind of color coordinate these. We know as you go across, electron shielding is constant. As you go down, there's more energy levels. As there's more energy levels as you go down, atomic sizes get bigger. As we go across, we can kind of explain this in terms of both of these. Nuclear charge is increasing, but shielding is remaining constant, so the atom is being pulled a little tightly, a little more wound, a little more tightly per the nucleus, so atomic size is decreasing. Again, ionization energy. Energy required to remove the outermost electron from an atom. It's increasing as you go over. There's more nuclear charge. Shielding is constant, so it's really hard to pull one of those electrons away. As you go down here, there's more shielding. So much shielding that it's really easy to remove that outermost electron. Plus the atomic size is getting bigger. So we have the 1/r² rule here. This outermost electron is going to be really far from the nucleus, so it'll be very loosely held, very easy to remove. And again, we have electronegativity, the attraction for electrons. As you go over, it's going to be very attractive for electrons. Because nuclear charge, again, is increasing, but shielding is constant, so you can really pull those electrons in. There's not a lot of repulsion or shielding. There's only 2 energy levels here, and only one is shielding. those atoms. And as you go over here, electronegativity decreases, going down. They don't really attract electrons. There's so much shielding, so much repulsion. The energy levels are getting so much bigger that you really can't attract electrons very strongly. And we saw again that the reactivity of metals increases as we go down. For nonmetals, the reactivity is going to decrease. Made another boo-boo. Starting to get annoyed. But for nonmetals, the reactivity is going to decrease. So again, we need to fix that. And going across, reactivity is going to increase. This is correct. And metals reactivity decreases. This is correct as well. So those are your periodic trends, and they're all in terms of Coulomb's law, nuclear charge, and electron shielding. So now, the fun part, you get an assignment. So this is a sodium atom, Na, number 11 on the periodic table. And it says that first ionization energy is the amount of energy needed to remove the outermost electron in an atom. So obviously it takes some energy to remove this electron. It takes a certain amount of energy, X. Second ionization energy, is the energy required to move the next outermost electron, which would be one of these in here. So the question for you is, will sodium have a higher or lower second ionization energy compared to its first ionization energy? Explain this in terms of the inverse square law, Coulomb's law, which is the inverse square law for electrostatics, and electron shielding. So I want you to tell me, if it takes a certain amount of energy to remove this electron, what can you tell me in terms of these things about the energy it would take to remove this electron afterwards? So that's your assignment. And this is Mr. Zapone. I'm out.